All right, welcome everybody. I set the solution to automatically release at 3:30, so that should be available to you now. I'll try and get your assignments graded as soon as I can. If you haven't heard already, we're going through kind of a crazy time in the Division of Engineering. We're trying to hire 8 new faculty members for the fall. And so usually what we do is phone interview between 8 and 10 applicants for each position. So that's 80 phone interviews. And then we'll bring 2, 3, maybe 4 applicants per position to campus. So that's 25 people who are visiting campus. So things are very busy this semester. And so I apologize if any of your grading falls a little bit further behind than I'd like. I'd like to get it back to you like tomorrow, because I usually have an uninterrupted block on Wednesday afternoons, but I'm filling my time with less enjoyable things than looking at your homework assignments, if that's even possible. All right. Yeah, we hope so. We may get a new construction management guy, for example, so, or girl. New hydraulics person? Maybe there's something you know that I don't. All right. All right, so you got my email about water gems. Now, it's not obligatory for you to have it installed by Thursday, but I'm going to give you just a short demo on how to draw a line. I think we already drew a line last semester, but I'm going to show you how to get water to move, actually, because all the calculations you did in fluid mechanics were static calculations. We're actually going to achieve the full measure of water gems creation and actually calculate head losses and stuff. So we'll do that on Thursday. Now the next assignment you have due is due a week from today, which is the same day we have our first exam. So I've already told you on the exam that if there's an Excel question, and there will be, that you'll be beginning with a blank worksheet, but then to mitigate your panic on that, you're allowed to bring your own equation sheet, and you could, for example, write column titles on that equation sheet if you wanted a little reminder on how to solve different types of Excel problems. All right, so I'll give you the equation sheet that's already there. There's a file on the MU Online that's called Sum Equations. And if you go to the Sum Equations file, then you'll be able to see what I'm providing. And then you can put whatever you want on your extra letter-sized front and back sheet of paper. That's a week from today. Right now, you'll be enjoying Exam 1. Any questions? All right. I was just, these notes change a little bit every semester. And 2 years ago when I taught this course, there was a big piece of news. Maybe it was 3 years ago. In the past, there was this big piece of news about a dam failure in Zimbabwe. And what it was is a dam that was under construction. And at the time of this incident, it had been under construction since 1998. So the gears of government moved slowly everywhere, especially in Zimbabwe. And so it was taking them a long time to get this dam built, and unfortunately they had a really wet weather event that backed up the water behind the dam much more than they ever expected during construction, and the water started seeping through. This was eventually going to be a concrete-clad dam, so it was going to be armored, and I think that was going to reduce the ability of the water to permeate through the core of the dam, but they hadn't got the concrete up yet. And so as the water levels rose, that created a higher hydrostatic pressure. And essentially, when you get a trickle of water, that will take some of the sediments with it. And then when those soil grains are gone, it'll cause a partial collapse. And then the water's moving faster, and the scour velocity gets more powerful. And it can take larger grain diameters downstream. And it's just sort of a chain reaction. So this dam in Zimbabwe failed because the water levels were too high. And you remember, we already previously have talked about the Mosul Dam earlier in the semester. What was the primary cause of concern with the Mosul Dam? The foundation was eroding. That's right. I mean, they built it on a rock that has about the strength and waterproofedness of drywall, essentially, like a really soft gypsum. And so they are constantly having to pump new grout down there to reinforce it. So this, dams can fail for a lot of reasons. This was a really big issue, and ironically, I was looking it up. It's the same Italian contractor working on this that finished the Saddam Dam in Iraq. So, I mean, these aren't the only two dams they've built, but ironically, they've had their hands in two pretty big, high-profile, serious failures. But nothing like that would ever happen in the United States, right? I mean, we're a cut above. I mean, American engineering would never have any sorts of issues like that. This is the Oroville Dam. I've actually been to the Oroville Dam. I've driven on top of that dam in a car. And so let's look at some of the pieces of this dam. The tallest dam in the United States, I think it's more than 700 feet high. Quite a spectacular view. You can drive up here and look down on all the agricultural fields at a lower elevation. They grow a lot of rice in the Central Valley, which is just kind of a nuts thing to be growing in such a hot climate, but it's made possible because there's plenty of water for agriculture as a result of trapping all the mountain runoff from the Sierra Nevadas. So it's a really tall dam, the tallest in the United States. There's water that comes through this power plant on the order of, I think they can pass maybe 30 to 40,000 CFS through the power plant. I think at 40,000 they actually have to turn off the turbines and they're not producing electricity anymore. They can get maybe around 3,000 CFS through a small fish bypass that allows migrating fish up and downstream through the dam. But then any more than that, then they have to start sending water down the primary spillway. And the primary spillway, it looks just like a super fun water slide, right? I mean, they had to kill the fun here with the big concrete blocks. I think that's to dissipate energy, to try and prevent any sort of scour that could potentially occur. As the water's losing 700 feet of elevation, it's going to be moving pretty fast. Now, this doesn't look it, but it's nearly a mile long. And so that's a very lengthy spillway. Here is what they call the emergency spillway. Now, I personally don't think they should call it the emergency spillway, because if water is going over the emergency spillway, then people are going to think it's an emergency, right? And ordinarily that wouldn't be true. In theory, you should be able to have water go over that emergency spillway and everything would be fine. But ironically, as soon as they started having water go over the emergency spillway, they realized that there was in fact an emergency because both spillways are failing at the same time. It's the case of when it rains, it pours, literally, right? They've got so much rainfall in the watershed upstream of this reservoir and dam that they can't send enough water through the power plant, so they've got to use the primary spillway. And then here's what it normally looks like when water's going through the primary spillway. But then last Tuesday, a week from today, they noticed something's off. Something's not right. Right? And so they turned, like they noticed it on Tuesday, a week from today, they turned off the water on Thursday. I think this is Thursday and this is Friday. I think this is just one day. So the Thursday picture's on the left, the Friday picture's on the right. So a little bit of a hole. Just to give you an idea of the scale of the hole, here's some guys climbing down into it. And this was Thursday. This is the Thursday hole that they're climbing into, because the Friday hole is no longer a hole. It's more of like a separate canyon or something. So this is them climbing around in the Thursday hole. For perspective, I mean, I don't even know why they're bothered. They're down there just because they can, not because there's anything to be learned by going down there. I mean, when there's a hole of that size, it's gone, you know? But, so people hear dam and emergency and failure, and they really start to panic. Remember, if we go back to the original picture, here's the dam. It's the spillway that's having a little bit of an issue. It's really separated from the dam. And so it's not the dam that's failing, it's the primary spillway they knew had some problems, and so they've kind of been tinkering around with the flow rate. They would slow down the flow rate because they don't want to damage the hole anymore, but then the water level keeps rising. And so the water level was rising so much that then they sent water over this emergency spillway. And so here's our fouled up primary spillway, and here's water going over the emergency or secondary spillway. So this is a really long weir, and you might notice that it just dumps water onto a hillside. And so it's not that same like nicely armored, carefully engineered chute that the primary spillway is. And I mean, it wasn't that carefully engineered, right? So, I mean, it was built in '68, so they were doing their best. They were probably using Casios or something. But so here's the secondary spillway, and the problem that they've had is that, okay, so it's concrete along the lip of the weir, but then the water just dumps onto this unarmored hillside, and it's really causing a lot of scour. Another view of the primary spillway. You notice here the discoloration. One of the stories that hasn't been getting as much attention as people having to evacuate their homes and so on is that there's a really important fish hatchery downstream of this location that had about 8 million salmon eggs and hatchlings, and they were able to evacuate 3 million of those eggs and hatchlings, but the other 8 million are stuck in water that has a much higher level of turbidity than they normally encounter, and apparently it's fatal for fish of that young age. They can't survive the water quality conditions, and so not only is it causing some economic devastation, it's also going to cause some real environmental trouble as well. All right, so just so that we're clear on the geometry of the situation here, here's the dam separated from the spillway, the regular spillway, and here's the emergency spillway that has some concrete, but then the water goes over a grassy field, over a road, and then just down the hillside. And the road isn't doing so good, yeah. But as the water comes over the emergency spillway, the force of the water when it hits that toe, it's just scouring the material. And so that's the failure that prompted everyone to say, we got to evacuate. We got to get people out of there. And in fact, they sent a tweet at one point where they were saying, we expect failure within the next hour, was because of what they saw happening here on the emergency spillway. It didn't end up causing that 30 feet of water rushing downstream, because if this emergency spillway had failed, then the height of the water behind it is between 20 and 30 feet. The height of the water behind the dam is around 700 feet. So, I mean, if the dam failed, it's like game over for a lot of Northern California. But the emergency spillway, it's bad, but yeah.
What was the effect on that event from the boundary drop? Did that like almost dry up because of the drought?
Yeah, if you look at pictures of this same reservoir last summer, the water levels were down to about 30%. And right now, the capacity of this reservoir is 3.5 million acre feet, and right now they've got 3 million acre feet in there. So it's very close to its capacity, but they can't let the water go the rest of the way because any additional water levels are giving them problems with the emergency spillway. Yeah?
I heard they were going to dump large amounts of rock
Mm-hmm.
that were flushing out the emergency spillway.
They're doing it. Yeah, they've got helicopters dropping rock into the void that was created with the emergency spillway. I don't have any pictures of the damage to the emergency spillway itself, but a lot of people are saying that it's unlikely the dam itself is threatened because of a really solid layer of rock that separates the spillways from the dam. Yeah, you can see the water levels are exposing, the low water levels are exposing. I mean, there's no way they could send water through the spillway at this point, right? But here is the photo of the emergency spillway in operation. I think this photo was taken on Sunday. And so it's showing water cascading down the hillside. And the concern is the scour that's happening here. So I found this posted online, someone speculating that that rock ridge is going to protect the dam from the damage to both the primary and auxiliary spillways. So both of these overflow spillways are having some trouble. This is an exaggeration that's kind of helpful to show like the separation between the primary dam, and even though the primary spillway is damaged and water spilling over in what looks like a pretty threatening way, it's still, that water isn't getting onto the dam itself. Kind of an interesting issue, right? The environmental consequences, you can see the highly turbid water here, lots of suspended sediment mixing with the cleaner water that's coming upstream. Apparently people were driving around doing a bunch of last-minute donuts before they had to pour water over the emergency spillway. First responders having the time of their lives, flying helicopters. All right. So I just thought, you know, it's been in the news lately, and this is a hydraulics class. We just look at some pictures there. Hopefully, oh, you can see it's basically a waterfall at this point. Hopefully things don't get worse because rainfall is predicted for later this week. So they can only pass about 100,000 CFS through the primary spillway. Any more than that, and they're worried that this scour could really get out of control. So, you know, this is a mass balance problem. The rainfall causes a flow into the reservoir, and they've just got to get rid of it so that the water levels don't get any higher and send more water over the threatened emergency spillway.
I've got it. They just need to drop a big old tarp on top of it.
A tarp? Yeah. 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 The big hole? They've estimated it's going to cost between $200 and $400 million to fill that big hole. So I guess they just got to, I mean, the only thing they can do is truck in fill, you know, pour it in there, and then do a better job with the concrete this time, right? I mean, there's no way around it. That water has to go somewhere. You know, as long as that dam is there, there's going to be events like this spring where they've got more water coming in than can go through the power plant. So they got to fix it. This isn't the first time that there have been real problems with dams. In the spring of 1983, I remember living in Utah when there was a similar thing, a real wet spring, and the Glen Canyon Dam was had a lot of scour through its penstocks. I'll show you some pictures of that. In fact, I might have already shown you last semester. Same kind of thing, guys climbing around in big caverns that were basically scour from concrete, scour from the erosive power of water. All right, today we're going to be talking about pumps. And the simplest kind of pump is a positive displacement pump, where each rotation of the pump moves a fixed volume of water. And this is a picture of a screw pump. And if you think about how it works, it's literally just like the kind of screw that you'd get in a hardware store. And it's surrounded by a trough so that you dip the end of it down into a canal, and with each revolution on the downside, you know, we're looking at this, it's going at an angle, so it's maybe at a 45 degree, and so it's like an angled trough, and then the rotating screw is pulling the water up through the trough, and then at the end it pours out. These are kind of a unique, rare thing. Positive displacement pumps aren't really common in the kind of hydraulic engineering practice that we're acquainted with. They're a little bit more common in lab applications, like in environmental research and medical research. We'll look at some diagrams of different types of positive displacement pumps in just a minute. But think about the energy equation. How many terms are there in the energy equation? 3? main terms, I guess, the energy can be in one of three places. I guess there's also the pump term and the minor losses and friction losses. I'm talking about head is V squared divided by 2G plus P divided by gamma plus Z. All right, so those are there's velocity head, pressure head, and elevation head. So this pump, how does it add energy to the system? Elevation. It's just physically lifting the water. So it's not changing the pressure of the water, it's open to the atmosphere. And it's not that it's adding velocity head, because as soon as the water exits this pump, it's just going to enter some sort of a reservoir or a tank, and it'll be motionless. So it's physically increasing the elevation of it. So it adds energy as Z. Here are some animated diagrams that show different kinds of positive displacement pumps. And in each one of these cases, there is a cycle, and with each cycle, a fixed volume of water is forced through the pump apparatus. The pump that I'm most acquainted with is a peristaltic pump. And the reason why I've used these before is in environmental labs, what you'll often have is flexible, like plastic tubing. And let's say that you want to pump water from like a container of some chemical, and you're pumping it into a reactor where you want some chemical reaction to happen. And you want a very, very slow but fixed flow rate to go into that chemical reaction. The peristaltic pump is basically, this is a wheel that's pressing against the tubing, and with each rotation, it's forcing a certain amount of water to go through the tubing. And the same principle is true for each one of these pump types, that the revolution forces a certain amount of water to move, and in this case, it's increasing the elevation of the water. In the case of the peristaltic pump, it's adding energy. I guess it's not lifting the water so much as, well, it would, depending on where you do the energy balance with the peristaltic pump. You know, if you have your source lower than the destination of the water. But these are kind of specialized where you wouldn't see this in a water distribution network, but instead centrifugal pumps are far more common. A radial flow pump where the water comes in on the suction side of the pump and it hits a spinning impeller. And the spinning impeller actually accelerates the water. And it has angled vanes that act a lot like the blades on a boat prop would. It increases the pressure of the water, and it exits the pump in a different direction. The high pressure side, the water gets accelerated outward, and it is collected along a, I guess you could say like a metal ring, and then it exits the pump through the top. And so what we sometimes think of as a pump is actually the combination of the pump, which is the impeller apparatus and the casing around it, and then this has to be paired with a motor to provide power to the drive shaft. So these are the most commonly used pumps for pipe networks. A very close relative is the axial flow pump. And an axial flow pump also is adding energy in the form of pressure. You know, back to the energy equation, this axial flow pump and the centrifugal pump, they're not increasing the velocity of flow on the inlet side to the outlet side, because think about continuity equation. Here are the blades of the axial flow pump. Here are the impellers, as they're called. The water that's on the suction side of the impeller has the same velocity as the water on the pressure side of the impeller. Because they have the same diameter, that shaft has the same diameter, which means it has the same cross-sectional area. And we know that in a situation like this, Q in has to equal Q out, because there's no place from the left to the right of that impeller that water could be stored. So anything that goes in has to go out of the pump. And so the velocity isn't increasing from the inlet to the outlet. Now, of course, when you turn the pump on, of course the velocity is increasing compared to when the pump was off. So I'm not talking about the velocity with respect to like the on-off state of the pump. I'm talking about the velocity with respect to position. So it's not in the velocity head that the pump is adding energy, and it's not in elevation either, because if this is horizontally oriented, the elevation is the same on the left and on the right. But what is changing is that there's a lot higher pressure on the upstream side, on the downstream side where the water's flowing to after it's added the energy. Here's a cross-sectional view of something that we have to be careful about, and that is the placement of the pump relative to where the water is actually coming from. So you can see that here, this is the water surface, and we know it's the water surface because it's got the ripples. The little triangle tells us it's a free surface of water where air is in contact with the water surface. And so the pressure at the interface of the atmosphere and the water is 0. And of course, pressure increases as we go down through the water. And now the water is going to go into the suction side of the pump. This strainer keeps branches and leaves and baseballs out of the pump. But then the water is traveling through the suction side. What happens to pressure in a pipe in the direction of flow? In a horizontal pipe, like this pipe is horizontal, this section is horizontal, and the water is flowing from the left towards the right. So what's happening to pressure in a horizontal section of pipe? Decreasing. Decreasing, because water flows from high energy to low energy, right? So just like the wind is going from high pressure to low pressure. So the point I'm making is that as the water is flowing through the suction side of the pump, the pressure is decreasing. And so one of the things we have to be cautious about when we're placing a pump is we don't want to have the pump too far away from the water source. It's okay if you have a really long run of pipe after the pump, but before the pump, you have to be careful about having too long of a run of pipe because you may have cavitation. And you'll remember when we talked about vapor pressure last semester in fluid mechanics, what we learned is that when the surrounding water pressure goes below the vapor pressure, then that's when boiling can occur. Boiling being the water going into a vapor. And so in a pump like this, you'll generally try and minimize the height difference between the water surface and the pump, because that delta Z can cause or contribute to cavitation, and so can a really long length on the suction side, because there's head losses. And any head losses that occur in the suction side of the pump may contribute to cavitation. So how to assess the threat of cavitation is something that we'll do in our second example today. But I want you to remember this diagram and remember that in the picture, the pump was pretty close to the water. Now, we don't have any dimensions, but it's pretty close. And one of the reasons why it's nice for us to have these radial flow pumps is that sometimes the water table is really far underground. And so this allows us to separate the motor from the impeller. And we can have the motor at the surface where it's dry and where there's air to cool down the motor and where it's easy to access the motor for repairs. I mean, just for a lot of reasons, it's easier for us to have the motor at the surface. And if we need to pump water from, say, an aquifer that may be hundreds of feet underground, we can just have a rotating shaft that goes down to wherever the water surface is, and then the impeller is down there. And so we don't have to put the pump all the way down, and we couldn't have the impeller all the way up. Because if the impeller was all the way up at the surface, then the water would cavitate before it was able to be lifted that high. So sometimes, depending on where your municipality gets its water, if it's groundwater, they may have pump houses throughout the city. And usually you'll see a big motor mount at the surface, but you may not always see the pump itself because the pump itself may be buried. All right. Ideally, we can calculate the power required by a pump in watts the units of P here is watts, by multiplying the flow rate in cubic meters per second by the unit weight in newtons per meter cubed and the pump head, which is meters. So that's the ideal pump equation in SI. In BG, we can get the pump equation in terms of horsepower by dividing foot-pounds per second by 550. That's the conversion factor between foot-pounds per second and horsepower. Efficiency has to take into account the two places where losses occur, and that is the pump itself isn't 100% efficient at turning mechanical energy into fluid energy, and so there is some efficiency factor that we apply for the pump, but then there's also an efficiency factor for the motor because it's not 100% efficient at turning electrical power into mechanical power. So we combine those two efficiencies together by multiplying them, and then you find the real pump power that's required by dividing whatever ideal pump power you calculated by the efficiency factor, and then that will tell you that you actually need to supply more electricity to the pump and motor than the pump and motor is putting into the water because of the losses. So just as a reality check, when you're doing calculations like these, make sure that once you've accounted for efficiency, you're supplying more energy to the situation, not less. So, you know, if you multiplied by the efficiency factor, then you'd be going the wrong direction. Pumps are efficient. I'm going to show you a figure in just a moment that kind of visually characterizes pump efficiencies, and they can be affected by the flow rate, the rotational speed, the fluid properties, and even the size of the pump. Usually a certain pump shape or a model will have lots of like siblings in its same model line. There will be a 2-inch diameter version of a certain pump style, a 4-inch diameter, a 6-inch diameter, and they'll have a lot of the same characteristics, and sometimes like the amount of head that they can generate is even represented on the same figure. But all of the energy that doesn't go into the water, most of that is lost to heat. There's also vibrations and noise, but the majority of the energy loss is in the form of heat. Okay, this is a really important figure. It is a typical pump performance curve, and there are a lot of pump problems on the FE exam, by the way. So this is important stuff. What this shows is that as you increase the flow rate that a pump is called upon to achieve, that the amount of head that it can add to the system decreases. So it's like a balancing act. The pump can add a lot of head, or it can achieve a high flow rate, or somewhere in the middle it can do a little of both, but it can't do everything, not all at once. The pump head, one way to think about this is that the elevation that it has to lift the water can be no more than the pump head. And this is sometimes called the shutoff head. It's marked on the figure here because if the pump is asked to add more head than this intercept, this vertical intercept, then it can achieve zero flow rate. But if I combine a certain pump with a system that has maybe just a little bit of friction, then it wouldn't need to add very much head. So I may be lower down on here, and so it would achieve a really high flow rate. But now if I made the pipe longer that the pump is connected to, that's going to increase the amount of friction that I have to overcome with the pump. And so if you're expecting it to do more work, then the flow rate's going to be decreasing. And oftentimes you can come up with an equation that describes the shape of that line. Here's just an example equation. Often they'd be provided by a manufacturer. They'd either give you an actual printout of the pump performance curve, or like an empirical estimation of how the pump behaves at a range of flow rates, which pump heads it can achieve. So the main thing you need to keep in mind is that The pump performance curve has a decrease in pump head as the flow rate increases. Any questions about this? So we combine pumps with a system. Here's a representation of a system where we're pumping from a lower reservoir up to a higher reservoir. So this delta Z can be no more than the shutoff head that is for this pump. Otherwise, the system isn't going to even get 1 liter per second. But if the delta Z is less than the shutoff head, it will get some flow rate. Now, how much flow rate? It all depends on how big the Z is, what are the losses through the pipe. You know, there are a lot of factors that can affect the flow rate, and we can put all of those factors into a rearranged version of the energy equation. And we can even graphically summarize what we call a system curve. Now, a system curve is a graph of how much head is required to achieve a certain flow rate. Now look at the shape of that typical curve. It's in contrast to the pump performance curve. The pump performance curve was that as the flow rate goes up, the pump head decreases. Now think about why that is in physical sense. As the flow rate goes up, then the pump simply isn't able to add as much head, because think about those blades as they spin. The difference between the pressure upstream and downstream of those blades is greatest when the flow rate is small. So do you remember we did a problem with the fan boat? And it was like there's a boat and it's got some fan blades, and it's it's powered by the air, and it can generate more power when it's not moving than when it is moving, because when it is moving, you've got the incoming air that is kind of like its ability to generate thrust depends on the difference between the incoming air and the outgoing air. And so when it wasn't moving yet, it had a lot of thrust because the incoming air was at 0 velocity. Here in the pump performance curve, a similar thing is at work. When you have a low flow rate, it's adding lots of pump head because the incoming water doesn't have much velocity yet. But the difference between the incoming and the outgoing pressures gets smaller and smaller. It can't add as much pump head. So here's the trend. You tell me, why is the curve shaped this way? Why is it going up for the system curve? Why does it require more pump head and like an exponentially increasing amount of pump head to increase the flow rate? Okay, you've got resistance. I'm going to amend what you said. You said from the reservoir. You've got resistance. I don't know that the reservoir resistance is changing. The delta Z is the same regardless of the flow rate. So as you increase the flow rate, what resistance is going up? Friction. So why would it be increasing exponentially though? Like what we're saying is that when your flow rate goes up a little, you need to add a lot more energy to achieve just a little more flow rate. Why is that? Mm-hmm. So you said it's velocity squared. I think you're probably saying HF is FLV squared divided by D2G. And so you're talking about friction losses are a function of velocity squared. You're exactly right. Very good. And so that's what we're seeing here, is that as the flow rate goes up, as Q increases, we're seeing a lot more energy losses, whether they're frictional or local losses. It's not the delta Z is the same, regardless of what the flow rate is, but we could do a graph of this system curve. And the system curve is just the energy equation. It's just the energy equation where point 1 is the lower reservoir and point 2 is the upper reservoir. And since the velocity in both reservoirs is 0, we canceled out the velocity head term of the energy equation. And since both of these reservoirs are open to the atmosphere, we are omitting the pressure head term from the energy equation, and all that's left is the delta Z between the two, and then the losses. So we've rearranged the energy equation to solve for H sub P. So this is the pump head required to achieve a certain flow rate when you've got a pipe length of L and so on, the parameters that are here. So does everybody understand why the system curve is shaped like this? What if I gave you a quiz and I said, draw a typical pump curve and a typical system curve? Would you know which one is shaped down and which one is shaped up? If you did, you'd do so great on that quiz. No, we're not going to have that as our quiz. Your next quiz is going to be about a couple of recorded lectures that I ask you to watch. I'm going out of town for a week. Not next week, but the week after. So you'll have 2 back-to-back recorded videos. And then the quiz that we'll have the Tuesday following that week will be based on those 2 recorded videos. Did you know you can watch the videos at 1.5 times speed? Have I showed you that tool? How you can play back it faster so you don't have to listen as long? Or slower, if you want to savor it. All right, so here are these 2 graphs. We've got the pump curve down, the system curve up, and what flow rate actually is there when you combine a certain pump with a certain system. It's when you graph them together and the 2 curves overlap. That's what we call the operating point. And essentially, that's the graphical solution. The paper solution is you're setting HP equal to HP. Because both of these equations, here's our typical pump equation. You know, it's in terms of HP and Q, right? So is the system curve, HP in terms of Q. So if you set the system curve equal to the pump curve and solve for Q, then you'll find that operating point. It's really easy to solve problems like this. You just combine the pump curve and the system curve together, and then it'll tell you what flow rate you're getting. Now, the challenge is that in the energy equation, you're supposed to have a friction factor F. But you don't know what the flow rate is when you're starting to solve this problem. So what we can do is begin our problem solving by assuming fully turbulent flow. In other words, Reynolds number is so high that it's just the relative roughness that dictates the F value. And then once we solve our first time around using that assumption, then we can calculate an actual Reynolds number and see how our updated Jane version of the F value compares to the fully turbulent assumption of it. So I'd like you to try that out. Here's the procedure. We have a certain system with a pipe length of 120 meters. The pipe diameter is 250 millimeters. It's made out of some material that gives us an equivalent sand roughness of 0.25 millimeters. The K value here, the large K, that is our local losses, the sum of our local losses. And then the elevation difference between the downstream reservoir and the upstream reservoir, 9.1 meters. So you can put all of those parameters into the system curve and set it equal to the pump curve. This is that same pump curve that came from the earlier diagram. So what we want to do is find the operating point. In other words, solve for Q. The first thing you're going to need to do, after calculating the area and so on, is use the fully turbulent flow assumption to find a starting point for your F. So we are given a pump curve by the manufacturer of the pump, basically a description of that trade-off between flow rate and pump head that it can achieve. And then the system curve we assemble based on the physical characteristics of the system, the pipe's length, its diameter, the material of the pipe, which defines the relative roughness, the K values, which are those local losses like valves and bends and so on, and the delta Z, which is the elevation difference. So here's the F value using fully turbulent flow. And then we have the friction losses and the local losses. And here it turns out that on a proportional basis, the local losses are bigger than they often are, 200 versus about 50. So it's good that we didn't ignore the local losses, as sometimes we can do. I had a good question as I was wandering around. Somebody said, when does the sum come into play here for the system curve? In our case, you just had 1L and you just had 1K. But if you had multiple pipe segments that were a different diameter, for example, then you'd need to calculate each of those segments separately. Because here in the denominator, you're having A squared times D. So you just have to take each segment that had a different pipe diameter and treat it on its own. And then combine them together. So it's okay to have multiple pipe segments, but it's just that the rate of friction loss is going to be different in a small pipe compared to a large pipe. So that's why we've got that sum sign there in the system curve. All right, so we find an equation that relates the system curve and the pump curve. We set the two equal to each other and solve for Q. So it should be about 0.24 cubic meters per second. And so we need to check the fully turbulent flow assumption just to make sure that this F value was valid. If it's not, then we'll use the new and improved F value to calculate a new system curve. The pump curve wouldn't be any different, but we may have a slightly different system curve, and then it would give us a slightly different flow rate. So let's see if that's necessary. What I did is I said, okay, here's my velocity. From that, I'll get the Reynolds number, and here's my K sub S to D. Rather than going to the Jane equation, it looks like I said I'll just look at the Muid diagram for that. So let's go back to a Muid diagram from earlier in the semester. That is that visual representation of Reynolds number versus relative roughness. And so my Reynolds number is 1.2 times 10 to the 6th. So here is that. And then the relative roughness is 0.001. So here's that. So I know I'm going to be okay if it's in the relatively flat part of the curve. This is the fully turbulent segment, and I'm just right at the beginning of that. So if I go over, it's basically slightly below the 0.02 line, so I'm calling that one good enough. But the people who actually ran the numbers in the Jane equation are saying that the F value was maybe about 1.5% different. And so, heck, if you're setting this up electronically or you don't mind doing the hand calculations, by all means, do the second iteration. But just for purposes of illustration, where you're learning how to set the pump curve equal to the system curve, I think that we can call this one converged. That would be the flow rate. So, any questions on this first example? Yes?
On the exam, you're going to expect us to go back and check the Reynolds number before Jane.
Yeah. Anytime you use the fully turbulent flow assumption, if you're really running low on time, you could say, and I need to check the fully turbulent flow assumption. But even better would be actually to check it and see if it's valid. And if you're doing a spreadsheet problem, for example, you can knock that out quick enough where it would be easy to reiterate a new F value. But exams are only 75 minutes, and I designed them trying to keep that in mind.
If we have to, but we're running short, can we write that we need
Yes.
to, and then just put it in the calculator and give the answer instead of writing out what it should be, showing what we put in the calculator?
I've had people take quizzes without even having a calculator, and they'd earn partial credit just by demonstrating that they knew what they needed to do without actually doing it. Doing the work is where you get all the credit, but if you knew you were supposed to calculate an updated F value, but you're running low on time, or for whatever reason didn't, at least show me that you knew that you were supposed to. That's the general principle. You're saying maybe do the calculations, but don't show your work?
Yeah, because you can just put it into
Uh-huh.
solve.
Yeah. Yeah. Okay.
Save like a minute.
Save a minute of writing. I hope it won't come down to that minute, because I'd sure love to see your work. Everybody's work, not just yours specifically, but all right. Show your steps when you've got time for it. And I think you will on the exam. I'm not going to make it overly lengthy. All right, so let's look at this figure. This is one of those manufacturer-provided visual representations of pump performance. So here's a pump performance curve. It's got a lot of stuff on there. It looks like just a bunch of chicken scratch at first glance. But this is actually showing both in traditional units on the left axis, SI units on the right axis. Here on the x-axis, we've both got flow rate in terms of cubic meters per hour and gallons per minute. Now, these numbers, 1,200, 1,600, 2,000, those are the rotations per minute. So if you have a certain pump and you're spinning that pump at 1,200 RPM, then this is its performance curve. Its cutoff head is 50 feet, and it decreases from there. The more flow rate you're trying to achieve with the pump, the less head it's able to provide. But if you spin that same pump, if you pair it with a different motor, and that motor is able to achieve 1,600 RPMs, well then suddenly you've got a lot more head out of that same physical pump. And so the first thing I wanted to point out is just the different RPMs and what effect that can have on the pump head. Another thing for you to notice is these curves that look kind of like contour lines. And what those are is those are the efficiencies. And so they give you a general idea of what's the efficiency from the input power to the output power that the pump is actually putting into the water. And so for instance, if we were operating this pump at 3,200 RPMs and 300 gallons per minute, so if we follow that 300 gallons per minute up to the 3,200 RPMs, then that would be 64% efficient. And so then you'd have an idea of how much power you need to provide to the pump. Now the NPSH, that stands for the net positive suction head, and it's related to cavitation. And it tells you how close to having the vapor pressure situation where the water is actually starting to boil inside the pump itself due to cavitation. We're going to talk about that next. Oh, by the way, I've got some hints for you, some homework hints. And in fact, I printed them out because I didn't want your memory cards to get full. So this is just easier, more clear. 2, 3. All right. This is for the assignment that's due a week from today. One more? All right, so on this problem, problem 924, they give you the system curve, but they give you a figure of the pump curve. And what you'll need to do is you'll need to digitize that. And what I mean by digitize is take some points off of the graph, and you will need to figure out what is the intercept of it, and then some coefficient like a C value, and so that you can set the two curves equal to each other. So in other words, it's kind of like a regression in a sense. You're going to have the system curve, but you need to come up with a pump curve before you can solve the problem. There's also a couple of other hints for other problems on the handout. We probably won't have time to go over them in detail, but I think they're self-explanatory, the rest of those hints there. Yeah, they're pretty simple hints. All right, so we may come back to this one a little bit later, but there you've got the handout. Hopefully that's useful. Let's talk about cavitation. We've only got 9 minutes left in class. Now, cavitation is the problem that can occur when you've got low pressure and getting lower in the direction of flow. So here is a picture of some tiny little vapor bubbles that are forming as the water is encountering the impeller. Because on the impeller surface itself, there's a high pressure side and a low pressure side. And those tiny little water vapor bubbles, when they collapse, when they get to the high pressure side, they can cause jets with a velocity of 110 meters per second and pressures up to 800 megapascals. And so they're small little vapor bubbles, but they have a lot of energy in them. And over the long term, those little cavitation bubbles can erode the surface of the impeller and cause a lot of physical damage to the pump. So here's how you calculate how far away you are from having cavitation as a problem. And the available net positive suction head is determined by the system curve. And what you start off with, this first term is related to the atmospheric pressure. And then all the other terms are decreasing how much head is available. And so the delta ZS is the elevation difference between the reservoir and the pump itself. HLS is the head loss in the suction side of the pump, of the pipe, so the water that goes from the reservoir just until it gets to the pump. And then P sub V is the vapor pressure. And so the bigger this number, the further away you are from cavitating. So here are the definitions for each of those terms. One thing I'll point out is that we're going to be measuring pressure and vapor pressure in absolute terms. And so for atmospheric pressure, we wouldn't put 0 here for the P naught. We'd put, if it's at sea level, 101,325 pascals for the atmospheric pressure. Now, we're comparing available and required. The required suction head is defined by the pump manufacturer. The idea, though, is that how much is required increases as the flow rate goes up. And let's look at that figure that we saw just a moment ago here. That's not it. This. That wasn't the one we looked at either. This one was. Okay, so as the flow rate goes up, this is how much head is required by the pump to avoid cavitation. So at a low flow rate like 225 gallons per minute, it only needs 8 feet of head. So you're far away from cavitation. But as the flow rate increases, it's requiring more and more head. And so the required versus the available is what we're going to be comparing. And if the available is less than required, then cavitation will occur. And so here is the diagnosis criteria that you're going to need to be able to apply. If the required suction head is more than what's available, then there's cavitation. Now, if they're equal to each other, that term is that it's at the point of incipient cavitation, which means it's just right about to cavitate. And so sometimes you'll be asked the question, for example, how high above the water surface can you place the pump? And so what you'd do in a situation like that is you'd set the required suction head equal to the available suction head, and then you'd solve for this delta Z to find out how high the pump could be, or maybe somebody would be interested in how long can the suction side pump segment, the pipe, be. And so the head losses on the suction side pipe are going to be increasing the amount of required, increasing the amount of available head. So let's do an example just to illustrate how this all works. We have, and we're low on time, so maybe I'll just show you this one rather than ask you to calculate it. Here's our system, and you'll notice the dimensioning here says that it's 4.3 meters from the water surface to the pump. Now, this system really has nothing to do with what's after the pump, because that's not going to cause the cavitation. It's just the suction side that we have to analyze, because the risk of cavitation occurs in the pump and in the pipe that's very close to it. So the delta Z here that's shown is delta ZS on the suction side of the system. Now, in problems like this, you'll usually be given the water temperature. or you'll have to assume a water temperature so that you can look up the vapor pressure of the liquid. And also, if it's an especially warm water temperature, like this is 40 degrees Celsius, which is pretty warm, then you're going to use a different unit weight of water. All right, so what it says is that this pump requires 3.5 meters of head to avoid cavitation. And so we're going to do a tally of how much is available. So this is just atmospheric conditions, and so how much is available starts with the pressure head of the atmosphere, and then we would subtract the elevation head, we'd subtract the head losses, and just to save time, to make the example a little simpler, we're saying those suction side losses are 1.6 meters. In a real-world situation, you'd need to calculate them by knowing the length of the pipe, the F value of the pipe, the flow rate. In other words, you'd use the Darcy-Weisbach equation. But here, they're just given. Like, let's assume that they solved the Darcy-Weisbach equation, and that's how much head loss you got. And then we also account for the vapor pressure of the water. So we go and take a look at how much is available and how much is required. All right, so here's the atmospheric pressure in absolute terms. So here's our first term, and then all the others are going to reduce how much head is available. So in the end, it has 3.7 meters of head available, and the required amount from the problem statement said the system requires 3.5. So under these conditions, there's not going to be any cavitation. But all we'd have to do to get cavitation is lift this pump up an additional 20 centimeters higher, and then it's going to start having cavitation. And then the impeller is going to start getting eroded. It would sound bad. It's just an altogether dangerous situation you want to avoid. So we're pretty close right now to having cavitation. And so the ways to prevent it would either be reduce the flow rate, and then that would decrease the head losses in the suction side of the pump. Sometimes to prevent cavitation, they'll make the suction pipe a really large diameter. And the reason why they'd have a large diameter pipe on the suction side is then that decreases the velocity and there's less head losses. And so that's just another way of minimizing the head losses. But the thing you really can't get around is this elevation difference. It's a hard limit. You know, at the most, even if the water had no vapor pressure and there are no head losses, if you have a delta Z that's higher than your pressure head term, then there would be no available pump head. So, I mean, that's essentially on the homework. You can get a quick start on that. You just apply the criteria of which is greater, the required or the available suction head. All right, so that's it for today. I'll see you on Thursday. We're going to continue talking about pumps, and I'm also going to give you the project assignment on Thursday. So I will see you then.